In this module, we will be working with proportions once again. And you guessed it, pen and paper will be your best friend right here. So let's go ahead and start talking about hypotheses with proportions. Now, these hypotheses that we will continue with will be used throughout all of statistics. What we have in a court of law is that people are presumed innocent until proven guilty beyond a reasonable doubt. Now, this can be referred to a lot of times as our initial hypothesis, or as we will call it, the null hypothesis. We can come up with an alternative hypothesis, which would be that they are guilty. Now, when we think about this right here, this is something we need evidence for. I want to make this very clear. The initial hypothesis, which is going to be called our null hypothesis, I think of null as nothing, as though you have no knowledge. Null means no knowledge. So if I tell you a person is on trial for a murder, well, are they guilty or not guilty? With no evidence, you would have to go with the null hypothesis and say, well, I have no evidence, so I would assume they are innocent. But eventually we might get evidence, or we might not. But if we had evidence, we might be able to show evidence for some alternative. This is done by collecting data for us. When we collect data, we might have enough evidence to reject our initial hypothesis. And if you think about this, when we go through this process in a court of law, they will either come to one of two decisions. Someone will be found guilty or innocent. If there is enough evidence, they will be declared guilty. We will call this rejecting our initial hypothesis, or rejecting the null. And going back to here at the start, our null was that they were innocent. We are going to reject that and show evidence that they are guilty. Very important wording right there. We are going to reject the null and show evidence for the alternative. Now, what does it mean when we don't reject the null? If we don't reject the null, well, my null hypothesis was that they were innocent. So if I don't reject this, I will continue to believe that they are innocent. And we're going to see this a lot throughout here, but it's very important to understand that the null is what you start out with. And you can't choose something like something that would be evidence-based, like, I think my brand of soda is better, that more people prefer it. You'd have to start with something that you wouldn't need evidence for, like, I think my brand of soda is just the same as every other brand of soda. And then you'd want to show evidence that more people prefer your soda. Because if you had no knowledge of any soda, wouldn't all sodas basically be the same? And you'd have to say, well, if I know nothing about these sodas, I would not know which is better. A lot of nuts and double negatives in there. So, moving on. This is our notation right here. Our initial hypothesis, as we said, is called the null hypothesis. The null hypothesis meaning we have no knowledge. The specific notation we will use is the null hypothesis is stated such that a population parameter is equal to a hypothesized value. Specifically speaking right here, a population parameter will be something like the true mean. We also call that the population mean, which is mu. For our examples in this chapter, we'll use the true proportion, or as we often call it, the population proportion, which is p. This hypothesized value is whatever we want it to be. The hypothesized value is usually something that we wouldn't need knowledge of. If we're comparing two sodas, we would have the hypothesized value that 50% of the population prefers our soda. And we don't really need evidence for that. If there's two sodas, well, people probably like one as much as they like the other, so it's probably a 50-50 split. It's not really an evidence-based claim. It's kind of a statement of no knowledge on which one's better. You can sometimes use historic values for these. If in the past, UT loses 12% of freshmen a year, we might say that we believe this year UT will lose 12% of their freshmen to kind of transferring or not coming back. And we would see right here that our hypothesized value of the true proportion of freshmen we will lose is at 12% or 0.12. This is often a historic value or a value of no knowledge when we use the null. We're just stating the true proportion of freshmen that we will lose this year is equal to 12%. And the 12% is taken from a value that we would believe to be true. And I know we said we have no knowledge here, but if it was 12% in the past, We don't know of anything that could have changed it. We're not saying, well, it's probably going up because of this or down because of this. It's kind of, well, it was 12%, so it's probably staying at 12%. Let's see if there's evidence that it's changed. And that is where we're getting at. Our main purpose right here is to show evidence for some alternative. The alternative is kind of what you're going for here. The null is what you start out initially believing. It's something you really don't need evidence for. It's what someone would believe generally without any evidence. And the alternative is what you want to show evidence for. We have three types of alternatives. We have what is called the two-tailed alternative, the left-tailed, and the right-tailed. This is the does not equals alternative, the less than, the greater than. Both of those names work out for these. When we talk about the tails, you'll see later on that it refers to the way we shade under the curve. So the two-tailed, the does not equals to, will have two tails shaded, where the less than, or the left alternative, and the right, and the greater than, the right alternative, will have one tail shaded each. So these bottom two are just one-tailed alternative, where the top one is a two-tailed alternative. And once again, they follow the same format. If you'll notice, it says alternative hypothesis states that the population parameter is not equal to some hypothesized value. This is the same hypothesized value we were using back here. So here we have the hypothesized value, and here we have it again. And although there are three listed on this screen, you won't be using all three at once. You'll only use one alternative. And think about that. Maybe UT puts into a new program to retain their freshmen. Would they want to show evidence that more freshmen are leaving after the new program comes into place? No. Would they want to show evidence that it has changed or it is not equal to that previous value? No. They'd want to show evidence that the true proportion, which is the parameter we're estimating, the true proportion of freshmen that are leaving UT is less than the hypothesized value. So if it was 12% in the past, we would want to show that it is less than 12% now. We want to show evidence of that. How are we going to do this? We will do this with p-values. P-values are our degree of evidence. That's very important. A p-value is your degree of evidence. Once we have both hypotheses, we'll need to collect data. We need to figure out if the null is true. In statistics, we can't ever prove something is true, but we can show the probability of getting our results in the sample data given that the null is true. That is what a p-value is. We assume the null is true for these tests that we're about to do. We assume the null is true, and then we find the probability of our results given the null is true. So think about this. With what we're about to do, if you assume the null is true, and then the probability of your results is very small, given the null is true, would you still believe the null? When it comes to p-values, we can use these distributions right here. As mentioned previously, the distributions we have will actually show us the values with the area shaded under the curve. This will be done by our less than, our greater than, and our two-sided alternatives. This area shaded underneath is called the p-value. We have very specific wording. The wording we use here is we can reject the null or fail to reject the null. And I do at times say I do not reject the null. I think it makes it easier for people to understand that fail to reject the null is simply saying I do not reject the null. Same thing right there. If it makes more sense to you, I have said to people, it's all right to say I do not reject the null. And that just means I fail to reject it. You're not rejecting it. So you can reject it or not reject it. And think about what that means here. If we start out believing something like someone is innocent, if you reject that, you're going to believe something else. To reject the null, I want to make this clear. To reject the null means that you will show evidence for the alternative. To fail to reject the null means you do not have evidence for the alternative, or rather enough evidence to believe the alternative. So when we reject the null, it's because we have evidence for the alternative. When we fail to reject the null, it's because we do not have evidence for the alternative. Evidence for the alternative is when the probability of getting our results, given that the null is true, is very small. This is the p-value right here. Oftentimes we use a cutoff of 0.05. So when the probability of our results is greater than 0.05, we would fail to reject the null. When the probability of our results or results more extreme, given that the null is true, is less than 0.05, we would reject the null, because our results would not be likely to happen given that the null is true. This is how we will do our testing. There are 4 steps. The first of the steps is to create your hypotheses. You will need a null and an alternative. The null states the true proportion of freshmen that UT will lose is equal to 12%. The alternative could be stated, and you would pick from one of these. The true proportion of freshmen that UT loses is less than 12%. And if you notice, I have 12% here and I have 12% down here. I am using the same hypothesized value. You'll pick one of these 3 alternatives, and you'll see these in the examples towards the end of the chapter here. One of these 3 will be yours, and oftentimes the problem dictates which one you will choose. So don't just pick it at random. If we were working for UT and we wanted to retain freshmen, we would want to show that the true proportion we lose every year is going down. We wouldn't want to show that it's going up, and to show that it's changing, or does not equal, we could say, is not really helping, because we could say, oh, it's changed this year. People would want to know, has it gone down? Has it gone up? And if we want to probably keep our jobs, we'd want to show that we are retaining more and more, which means the true proportion we are losing is going down. We need to pick a statistical model to use. This model that we're going to use is going to be based on a distribution. So we've seen this before, and we are going to use the z-distribution right here to help explain the data. This is going to allow us to use the empirical rule or to use z-scores. Right here we see our ability to create a z-score. This is a one-sample z-test. Right here we can actually find the z-score for our sample proportion given some null proportion. The null proportion is the hypothesized proportion that we first came up with. And if you notice right here, the standard deviation of this distribution is based on the null proportion. The reason for this is because the null proportion right now is believed to be the truth. The truth is also going to be the center of the distribution. At this current time, we believe the null is true, and we want to figure out the probability of our results. So we're going to look at how far away our sample proportion is from the hypothesized proportion, and then find that in terms of standard deviations. We're going to standardize the difference up here. From this, we need to calculate our p-values. This can be done right here with the David M. Lane applet. It can be done with the empirical rule. For this one, I would highly suggest on the test knowing the empirical rule. It always comes into good use. You can estimate p-values and often know on z-tests when to reject. And that time of when to reject is oftentimes when we have a z-score less than -2 or greater than +2 if we're using an alpha of 0.05. More on alpha in a moment. Finally, the last part of our test here is to make a conclusion. And we spoke about this before. We will either reject the null or fail to reject the null. Those are our only 2 decisions. We would never say, and I want to make this clear, we would never say I accept the null. Because in statistics, we only show evidence of stuff. To say accept kind of means you've proven something. To say I accept this. We can oftentimes fail to reject 2 different null hypotheses or show evidence for 2 different alternatives. So the word accept is a very bad word in statistics because you can't accept 2 things to be true. But you can show evidence for 2 different things. With the 3 alternatives we have, once again, we have the 2-sided alternative as I spoke about before. Now the 2-sided alternative can be shown visually right here. we have the area being shaded on the left side and on the right side. This is because we observed a p-hat of 0.17. This is the sample proportion. The null proportion was equal to 0.20. This is the center of our distribution. The standard deviations were calculated from the null proportion. So with this in mind right here, if we shaded below 0.17, we would get this area. If we reflect this, we would shade above 0.23. If you'll notice, it's symmetric. We're going to shade above and below equal distance away. So if we found the area down here, we could just double it to the area up here. Now think about this. If we were to do a one-tailed alternative, just a left tail, you would go to where you observed your results. This is our actual observed results. This is our sample results, p-hat. And you would just shade below. Right here instantaneously, we can think about the p-value for our less than test. Our p-value for our less than test is 0.067. The two-tailed test is always double your smallest test. Now, if you shade to the left of this value, you get 0.067. If you shade to the right of it, you'll get 0.933. And think about it for a moment. This shading right here to the left and this shaded to the right, and I'm going all the way to the right. I'm not stopping here. I'm going all the way to the right. If you go all the way to the left and all the way to the right, you shade 100% of the curve. So what did we just learn? We learned that the less than and greater than alternative always add up to 100% of the curve. So if the less than alternative is 0.80, the right alternative, the greater than, would be 0.20. They add up to 1. If the less than alternative is 0.01, the right alternative is 0.99. Now think about that. 0.01, 0.99. What is the does not equal alternative? If this is 0.01 and this is 0.99, the does not equal is double the smallest, which would make this 0.02. Try another one. If this is 0.96, what's this one going to be? Since they have to add up to 1, it's 0.04. So what will this one be? This is always double the smallest. So 0.96, 0.04, and then this is 0.08. Now, as we said, we'll only be using one of these at a time, but statistical software will display all of them for you. Here's our one-sided alternative we spoke about, and we can see just shading the area to the left. And as we said, if we shaded the area to the right, it would just be 0.933 over here. So our smallest p-value is over here. Now the alpha value that we spoke about, we can decide any value we want for it. And we'll speak about it here just briefly. The alpha value is very important because it's our degree of evidence that we will accept. So if you're working for medical research, you probably want to pick a very low alpha value. And the reason for this is because you want more evidence. The lower the alpha value, the more evidence you require to reject the null. We will reject the null when our p-value is smaller than alpha. We have been using a 0.05 alpha, and we generally do, to reject the null. This is our degree of evidence. And think about it. You have to land further away to get smaller p-values, which means here's your null. This is where you thought you would land. So the further away you land, the less likely you are to believe this right here. If you were to land right here, would you still believe 0.2 to be correct? I would, and that's why I'd fail to reject it. But if you were to land all the way over here, really far away, would you still believe 0.2 is correct and that this happened by chance? And I'm pointing right here at 0.14. No, the probability of this is something like 0.15%, 0.3%, and it's very unlikely that this value would happen by chance given the null is true. So what do we do to the null if we land over here? We reject the null, and we show evidence that the alternative is that the true proportion is less than. This value that we got in this example right here would not allow us to reject the null because the probability of our results, or results more extreme, given that the null is true, is 0.067. And that's not low enough. We want a 0.05 to reject a lot of times. when you do your research, you have to decide your value of alpha before doing your tests. People will want to decide it afterwards because they'll be like, hey, no, we came close. And we could look back here like, let's use a 0.07 value because then I can reject. If I say I'm going to use a 0.07 alpha, then I have evidence here, and I can say I reject the null with an alpha of 0.07. Well, that's not the fair way of doing it because you're getting results just because you want them. If you had to decide beforehand, you would have probably picked 0.05, and then you would not have results. So let's look here at a study done with the Wall Street Journal. What we have here is that an older device had blood clots of 7%. So with this new device, we're probably going to use it if we do not have evidence that the blood clots with it are more than the old device. So the true proportion we would assume right now is 0.07. Do we have evidence that the true proportion is greater than 0.07? And listen to how I spoke. Let's go back to our null and alternative here. The null and alternatives are very important. I said the null states that the true proportion of people who will get blood clots from this new device is equal to 0.07. The alternative states that the true proportion of people who will get blood clots from this device is greater than 0.07. Do we have evidence for the alternative? And this time we do not actually want evidence for it because we probably want to use the new device. So let's go back here and we see it. This is exactly what we stated before. The null states that the true proportion of people who will get blood clots from this device is equal to 0.07. The alternative states that the true proportion of people who get blood clots from this device is greater than 0.07. Second time stating it. Very, very important to be able to write these out. So what do we have? We go out and we sample 871 people. Of those 871 people, 70 people experience blood clots. This is a sample proportion, because it came from a sample size, of 0.08. Now we know this is 1% difference, but we haven't standardized it. We haven't standardized this difference. First, let's check our conditions to make sure we can actually use the normal model. And these are very similar conditions to what we've done before. Did we randomly select these people? Yes, we did. Do we meet the 10% condition? Yes. 871 is less than 10% of all people that will be using this device. And that's kind of an assumption, but it might be safe to assume. The final is the success-failure condition. Now this is based off the null proportion right here. This states the sample size times the null proportion. The null proportion was 7%, and we sampled 871 people. So if I do 0.07 times 871, that is greater than 10. And NP plus NQ, and in this case NP naught plus NQ naught, will equal to 871. So we can see here if I do 871 times, both of these numbers added together would equal 871, and 93% of 871 is much greater than 10. There we go. We have conditions checked. That means the normal model is appropriate. And now we can do some z-scores. If you notice up here at the top, we once again have the difference of 1%. We observed 8% in the sample proportion, and we expected 7% according to the null proportion. Once again, I want to make this clear. The standard deviation of this distribution is based on the null proportion, and that's the complement of the null proportion. So this is 0.07 and 0.93 right there as we see. P naught and Q naught are right here and right here. So it's just they add up to 1. The bottom portion is the standard deviation for this distribution. This z-score is only 1.16, and that's not a very big z-score. We can see it over here on the David M. Lane applet. The David M. Lane applet shows us how far away we fell, and we shaded in the area. The answer is the probability of our results or results more extreme given the null is true is about 12.3%. This is not small enough for us to reject the null. This device could have around 7%. We do not have evidence. And you might think that sounds crazy, but it's probably just fluctuations is what we're saying. Because if the device really is 7%, well, if your friend tells you I'm horrible at basketball and I'm a 7% free throw shooter, if they made 8% of their shots, would you say that you still believe them? This was within the bounds of what we would expect for 7%. It wasn't too extreme. So we will continue to believe. We will fail to reject the null. This was not beyond our cutoff. We would have needed a p-value below 0.05. So as we said, we fail to reject the null. There is not sufficient evidence. So when you fail to reject the null, you will not show evidence for the alternative. So you can just leave it at that a lot of times. I fail to reject the null, and you could say, I continue to believe that the true proportion of people who receive blood clots is 0.07. Because remember, your null is at the center of this distribution. At the center right here is 0.07. Because it's like our z-score formula. This is the mean in the z-score formula. It's the center of the distribution. It's observation minus mean over standard deviation. Very similar formula. Observation minus mean over standard deviation. Sample proportion minus null proportion over standardizing factor. It's just like our z-scores from an earlier chapter. And you'll see this with the t-test and things to come later on. It's the same type of formula. So going on right here, let's try another example. So in this example right here, we won't actually do some groups, but you can do it on your own with me right here. So let's try this out. The developer of a new sports drink claims to have done considerable research and reports that 65% of consumers prefer the taste of the low-calorie sports drink over your product, which is the best-selling low-calorie sports drink on the market. You feel that their claim of 65% prefer the taste of their product over yours is grossly overstated. You plan to pay an independent testing agency to conduct some unbiased taste testing comparisons. You plan to pay an independent testing agency to conduct some unbiased taste testing comparing. You plan to pay an independent taste testing agency to test this out with the two drinks. So what are the null and alternatives right here? So with this in mind, they're stating it's equal to 65%. It'd be that the true proportion of people who like their sports drink is equal to 65%. And we could try to claim something different. We could claim it's less than. We probably don't want to claim it's greater than that because that would not look good for us. We could claim that it's not equal to that also. Let's go with the claim that it is less than that. And we're saying, no, your figure's too high. It's less than that. So we go out and we do the test right here. And we need to do what is our sample size of 327. And we need to find out with 187 people saying they like it. And they like the competitor, so this is not good for us. This is 57%. I'm going to copy it right here. So the sample proportion is around 57%. There it is right there, 57.18. And I got that from number of people who said they liked it, which is X over N, which is number of people we sampled. We need to randomly select these people. Any problem would need to state that these people were randomly selected. That's very important. We have the 10% condition that these people are less than 10% of all consumers. And the success failure condition here can be checked given that they claim 65%. 65% of 327 is way more than 10. And 35% of 327 is way more than 10. So we're good. We're good on that. That was NP0 and NQ0. Both are way bigger than 10. So with this in mind, we need to calculate the z-score. So I left this on the calculator for a very specific reason right here. Right now, I have p hat. So I'm going to copy this and have it on here still. Now I'm going to take, this is p times q. And then we need to find n. N was 327. So I did p times q over n square root. So that was p times q over n square root. And now what I'm going to do is I'm going to go to a notepad very quickly. And I'm going to paste in my numbers so I don't lose them. So this is p hat right here. And then I have right here, here's the standard deviation. And now let's go ahead and do p hat. Let's put in p hat minus p naught and we get a negative because we fell below. So now we have p hat minus p naught, and now I'm going to divide it in terms of standard deviations, and there's our z-score. We fell almost 3 standard deviations below the mean of this distribution. And if you remember from outliers, 3 standard deviations is very far below. So let's look at this on the David M. Lane applet. Okay, we're on the David M. Lane applet now. If you notice, what we have is very far below the mean. And the probability of our results or results more extreme, well, it's basically, if you remember from the 68, 95, 99.7 rule, it's literally almost 0.0015, which is almost the 99.7 rule. So the empirical rule really works out. The probability of our results or results more extreme, given the null is true, well, it's not very likely. So we're going to say to them, your claim is grossly overstated. We would say, nope, not happening. What you've told me is a fabrication. What we've seen in our practice is, we'd have to say, unfortunately, we think you might be leading the market, but not as much as you claim to be leading the market. So they still can hang that over our heads, but we do not have the grandiose claim that they're making that they have 65% of consumers preferring theirs. Now, they might come back and say, oh, well, you didn't randomly sample people. And that could be a problem because maybe we went to the wrong spot and we didn't see the right kind of variation that exists. So lots can be taken into account with this. Now, one thing I want to mention is you can do all of these in the TI calculator. The TI calculator, the 84 series and many of them, have the stat button. Under the stat button, you can go over to tests, and it's under the one prop z-test. If you're over there on your TI calculator under stat test, go over to one prop z-test. The first things it asked you for is the null proportion, the null proportion being 0.65. The next thing it asks you for, let's go back, is the number of successes, which is x, which here is 187. Next, it asks you for the sample size, which is 327. And then it asks you for the alternative, which I'm going to select the less than alternative. It says true proportion, and then it has 3 choices, and I'm going to pick less than the hypothesized proportion. So let's go ahead and hit calculate right here. And under the calculate, I believe we get the exact same z-score, just double checking. My z-score that I calculated was negative 2.96228, and that's the exact same z-score. And virtually identical p-value, because it probably carried out more decimals than I did, or David M. Lane is not calculating it perfectly. Darn you, computer. But still, we're within thousands or tens of thousands of the same p-values. And we would reject the null right here, and we would say we have evidence that the true proportion is less than the claim of 65%. And that does it. Email me if you have questions.